Hey guys, this is part 2 of my video on 14.3 partial derivatives. I did a bunch of problems in the other video, and here I'm going to do even more of them. There are really a lot of different cases, lots of different kinds of problems that we have to work with. But they are important, so we're not skipping them. So before I do this next problem, I wanted to remind you of a couple of things from Calculus 1 that you might not remember. Just a little bit of information here. So what I wanted to talk about was a couple of derivatives. Remember, if you take the derivative d dx of x to the a, this is called a power function. So for that one, we're going to use the power rule. And that's the one that we've been dealing with, where a is a constant. So if a is a constant, and you have the derivative of x to the a, you do the power rule, which means you bring the constant out front and you decrease the exponent by 1. So that's going to give us a times x to the a minus 1. That's the power rule. Power rule. Okay. But we already knew that, so why am I bringing this up? Well, it's easy to confuse the power rule with exponentials. So what about the derivative of exponentials? Well, if you're taking the derivative of a to the x, where a is a constant, you don't use the power rule. Instead of the power rule, what you do is, since the base is a constant and the variable is an exponent, this is an exponential function. It's different from a power function. And the formula for this one is ln of a times a to the x. Okay, and the reason I'm bringing these up is it's easy to get these confused, particularly when you're doing the next problem I'm going to do from your homework. So make sure you don't get them confused. So what's the difference between these two functions? The first one's called a power function, and for that one you use the power rule. You bring the exponent out front and you decrease it by 1. That's the power rule. But then for the second one, instead of using the power rule, you're actually taking the derivative of an exponential function. So that's a different rule. I don't know what to call that one. I'll call it the exponential function derivative. And it works in a different way, because here the base is the constant, whereas this one, the power is the constant. And so if the base is the constant, it's ln of a times a to the x. And remember, the derivative of e to the x is just e to the x. That's a special function. So the special case is d dx of e to the x is just e to the x. That's the special case. That's e is called the natural base. Okay? But don't get these two functions confused, the x to the a and the a to the x. It's very easy to confuse them, but you got to keep them straight in your head. So you look at which one is the constant. If the exponent's the constant, you use the power rule. If the base is a constant, you use the exponential function derivative rule. Okay? So now that we got that stuff down, now we're ready to tackle a pretty challenging problem on partial derivatives. Okay, so example, find del f del x, and del f del y. It's like finding del taco, only it's finding del f del x and del f del y. So what we got here for our function is we have f of x comma y equals 5 times x to the 6y. Okay, 5 times x to the 6y. So, this problem looks like it would be easy, but it's only easy if you know exactly what you're doing. It's pretty easy to mess it up, honestly. So let's start with del f del x, or partial f partial x. So for this one, the other variable is constant, so here y is going to be constant. Okay, and then we have to be careful. So since y is constant, that means the power 6y is constant. So this is constant. So since the power is constant, but the base is a variable, this is a power function. So we use the power rule. So how do I know we're using the power rule? Well, I said use the power rule if the exponent is a constant. So looking here, the exponent is a constant, you use the power rule, which means you bring it out front and you decrease it by 1. Okay? And then the base is not constant. We said y is constant, but the base is not constant here. So that's why we're using the power rule. So what we're going to do is we're going to factor the 6y out front. So we're going to have 5 times 6y times x to the 6y minus 1. Now why is it 6y minus 1? Well, because we're doing the power rule, and remember, you bring the exponent out front, and then you decrease the exponent by 1. And then we can simplify this a little bit. So 5 times 6 is 30. So our partial f partial x is going to be 30y x to the 6y minus 1. Okay? 30y x to the 6y minus 1. Alright, so let me box that. So there's our del f del x. And then the next thing we need to find is del f del y. Del f del y. So for this one, the other variable is constant, so here x is constant. And we're taking the derivative with respect to y. Okay, so let's take a look back at our function again. Since x is constant, that means the base is constant, but the exponent is a variable. So the exponent is 6y. So remember, if your base is constant and your exponent has a variable, then it's an exponential function. And so we're going to use this formula. So it's going to be ln of the base times the base to x. Okay, so it's going to be, we're going to have 5 times ln of the base, which is x. Now remember, x is a constant, so that's why it's 5 times ln of x times x to the 6y. Okay, so this time, what did I do? Drag something around. Put that back here. Okay, so what I'm trying to say is this time, our base is the constant, and our exponent is the variable. Okay, so we're actually using the exponential function rule. So here the base is constant, and the exponent is changing. The exponent is a variable. So we use, this is an exponential function. So that's how we use the second rule that I wrote down, which is ln of the base times the base to the x. Well, in this case, it's ln of x times x to the 6y. Okay? And then there's a specific order that they write in my math lab. So they write the constant first, and then they write your power, so x to the 6y. And then they write your natural log last. So for our answer, we're going to have this in the form 5x to the 6y times ln of x. Okay, and that's going to be our partial f partial y. So it's a little bit tricky. It's not that the problems are long, it's just tricky because it's easy to confuse which case you're in. Alright, cool. So since we've seen pretty much all of the cases for functions of two variables, I want to move on to partial derivatives of functions of three variables. Now it sounds intimidating, I know, but functions of three variables just mean that when you're taking a partial, two of the other variables are going to be constant. Okay, so you're going to have a function of x, y, and z, and then if you take the partial derivative with respect to x, your two other variables, y and z, are both going to be constant. So it's not quite as intimidating as it sounds. So let's take a look at this. Okay, so example. Find f sub x, f sub y, and f sub z. Okay, so first of all, we have some new notation here. So what we're going to have here is a function of three variables. So this is going to be f of x, comma y, comma z. And on this particular problem, our function is sine inverse of 5xyz. Okay? Sine inverse of 5xyz. And what they want us to find is the partial derivative with respect to x, with respect to y, and with respect to z. So they're using a new notation here. So this f sub x, f sub y, and f sub z, that really just means the same notation we've been talking about in the other problem. So f sub x just means partial f, partial x. Okay, that's all it means. And f sub y means partial f, partial y. Okay? And the last one, of course, f sub z is going to be partial f, partial z. Okay, so del f del x, del f del y, and del f del z. Okay, but these problems can take a while because you actually have to find three derivatives. But the basic idea is for each derivative, you're taking the derivative only with respect to that variable, and then any other variables are just treated as constants. Okay. So let's go through this. First of all, before we even do the problem, I just want you to recall the derivative of sine inverse. Okay, so recall, this is from Calculus 2, I believe. So recall d dx of sine inverse of u. It's easy to forget these, but this is one of the inverse trig functions. If you take the derivative of that one, it actually turns out to be 1 over the square root of 1 minus u squared times du dx. But instead of being du dx, it's going to be partial u, partial x when we're doing these problems. Okay, so that's a formula that we're going to be using in this problem. So the derivative of sine inverse of u is 1 over the square root of 1 minus u squared times du dx. But we're going to actually be doing it for all three variables separately. Okay? So let's start with partial f, partial x. So the way they're writing it is f sub x, but that's equal to partial f, partial x. And just like with two variables, if you're taking the derivative with respect to x, the partial derivative, the other two variables are going to be constant. So here, the other two variables are y and z. So here, y and z are treated as constants. Okay, that's actually what a partial derivative means, is you treat all the other variables as constants besides the one that you're taking the derivative of. Okay, so partial f partial x, we're going to treat y and z as constants. Okay, so here, y and z, and also the 5, those are all constants. Okay, so we're going to be using the chain rule. And remember, the chain rule says you take the derivative of the outer function, inner left alone, and then you multiply that times the derivative of the inner function. So here, the derivative of the outer function, which is sine inverse, that's going to be 1 over the square root of 1 minus u squared. Well, here u is this big thing here, 5xyz. So we're going to have 1 over the square root of 1 minus 5xyz squared. Okay? That's just using the formula for the derivative of sine inverse. And then you have to have times the derivative of 5xyz. That's the chain rule. And here that's going to be times partial u partial x. Well, what does that mean? That means we take the derivative of the inner function. So here the inner function is 5xyz, but 5, y, and z are constants. So the only thing that's going to go away is the x. So this is going to be times 5yz. Okay? And then to finish writing it the way they do on MyMathLab is you go ahead and you move the 5yz to your numerator. Okay, so let me go ahead and put that, instead of the 1 on top, we're going to go ahead and write a 5yz up here. Okay, and then the other thing that we can do to simplify this is we can square the 5xyz, okay, which basically means we're just going to be distributing that square to each factor. Okay, so we distribute that 2 to each factor. All right, so that's going to give us our answer, which is going to be 5yz on the top, and then on the bottom we have the square root of 1 minus 25 x squared y squared z squared. That's my cat, Max. He has food, but he's still complaining. Okay, so we got 5yz over the square root of 1 minus 25 x squared y squared z squared. So that's our f sub x, or partial f partial x. Okay, so I'll box that one. So then let's go ahead and find f sub y and f sub z. So let's find the partial with respect to x. We already found the partial with respect to x. Now we're going to find the partial with respect to y. So f sub y is the same as partial f partial y. Okay? And once again, it means the other variables are treated as constants. So here the other variables besides y are going to be x and z. Okay, so here x and z are constant. Okay, x and z are constant. Okay, so partial f, partial y. Well, if we go back up to our original function, now x and z are constants. So just slightly different from the last one we did. But it's almost the same setup. So once again, we're going to be using the chain rule. So the derivative of sine inverse is 1 over the square root of 1 minus u squared. So we're still going to have 1 over the square root of 1 minus u squared, which is going to be still 25 x squared y squared z squared, right? Because u is still that 5xyz. And then we have this times the derivative of the inner function. So times the derivative of 5xyz, where x and z are constants. So what's going to go away is the variable, which is y. So we're going to be left with the constants, which is 5xz. Okay, so we're going to have this whole thing times 5xz. And then to write our answer the way they do in my math lab, we're going to go ahead and move the 5xz up to the numerator. Okay? So I'm going to replace that 1 with a 5xz. And then we've got our second derivative here. I probably shouldn't call it second derivative, but this is the derivative with respect to y. So partial f, partial y. Okay? Okay, cool. And then let's do partial f, partial z, or f sub z for our last one here, for this problem. So f sub z, or partial f, partial z. Here, the other two variables are going to be constant. So since we're taking the derivative with respect to z, the other two variables are x and y. So x and y are going to be constant. Okay, x and y are going to be constant. But the setup is pretty similar to what we were doing for the other parts. So this time, x and y are the constants. So we got 5xy, that's the constants, and then z is our variable. But the rest of it's going to be the same. So we're still taking the chain rule. So the derivative of the outer function, sine inverse, is going to be 1 over the square root of 1 minus 5xyz quantity squared, which we said was square root of 1 minus 25x squared y squared z squared. Okay, so here we've got 1 over the square root of 1 minus 25x squared y squared z squared. Once again, that's the formula for sine inverse. The derivative of sine inverse. And then we multiply this times the derivative of our inner function. So our inner function is 5xyz, where 5xy are constants, and we're taking the derivative with respect to z, so the z is going to go away. So we're going to be left with 5xy. Okay, so this whole thing is times 5xy. And then to get our problem in the same format that they have for my math lab, we go ahead and we move the 5xy up to the numerator of our fraction. Okay, so we replace the 1 with 5xy. So then we get a 5xy up here, and we're good. So there's our partial f, partial z. And notice these partial derivatives almost look the same for this problem. The only difference is the variables in the numerator. Sometimes your derivatives will look very similar. Other times they'll be different. But with this one, a lot of them look quite strikingly similar. Alright, so cool. So I think I'm going to do maybe just one more. I wanted to do a problem that has some different letters, some Greek letters, because many of you will be studying science or are already studying science. And particularly in physics, Greek letters show up a lot. So let's do an example. In this example, they're asking us to find the partial derivative. Find the partial derivative with respect to each variable. Okay? Find the partial derivative with respect to each variable. Okay? And here our function is h. And this is h of rho, comma, phi, comma, theta. Rho, comma, phi, comma, theta. I'm a little rusty on my phis. I think that's a phi. Yeah, that looks more like a phi. Okay. So this first one looks like a p. That is rho. The second one also sort of looks like a p, but is more of a curly shape. And this one's called phi. These are all Greek letters. And then the last one you probably already recognize. That one is theta. Okay? And you can always look those up on Google if you want to read more about Greek letters. But those are some of the 3 most common Greek letters that show up a lot in physics, for example. Okay? And here our function is going to be rho sine of phi cosine of theta. Okay? Rho sine of phi cosine of theta. And people draw phis in different ways. If you look on your homework, the phi looks more like this. It almost looks like a little, leaf or something. But when I write my phis, I think the way most people write their phis is more like that. Okay? Alright, so rho sine of phi cosine of theta. Now once you get used to the weird Greek letters, this is actually a pretty easy problem. Now, to find the partial derivative with respect to each variable, they want you to do each individual variable. So let's start with rho. So let's start with partial h, partial rho. So this one, the other 2 variables are going to be constant. So here, phi and theta are going to be constant. Phi and theta are constant because those are the other 2 variables. Okay, so if phi and theta are constant, that means sine of phi and cosine of theta are both constant. So all this right here is constant. So really the only thing that we're taking the derivative of here is the rho. And the derivative of rho with respect to rho is 1. So all we're going to be left with are the constants. So we're going to get sine of phi cosine of theta. Okay, sine of phi cosine of theta. Alright, and then to finish this problem, we got to do the other derivatives. So we just found the derivative of h with respect to rho, partial h, partial rho, and now we have to do the other 2 variables. So let's go on to phi. So if we want to find partial h, partial phi, partial h, partial phi, then that means the other 2 variables are going to be constant. So that means rho and theta are both going to be constant. Okay, rho and theta are constant. So what's that going to look like? Well, sine of phi is part of our variable, so that's not constant. But the rho and the cosine of theta are both constant. So the only thing we're taking the derivative of here is the sine of phi. And the derivative of sine of phi is going to be cosine of phi. And then the rest of it just stays because it's constant. So here we're going to have rho cosine of phi, sine of, what was it, cosine of theta? I already forgot. Cosine of theta, sorry. Okay, so what we did there is we took the derivative of sine of phi, but we left everything else as a constant, so nothing else changed. Okay, so that's our partial h, partial phi. And then for our last one, we're going to be doing the last variable, which is theta. So we're going to do partial h, partial theta. And you should be getting used to this by now. The other variables are always going to be constant. So what are the other variables here? The other variables are rho and phi. So rho and phi are constant. Okay? Alright, so if rho and phi are constant, then that means the only variable is theta here. So the cosine of theta is not constant, but everything else is. So we're not going to change the rho and the sine of phi. We're only going to take the derivative of cosine of theta. And remember, the derivative of cosine is actually negative sine. So we're actually going to get negative sine of theta here. So for our answer, we're going to get negative rho sine of phi sine of theta. Negative rho sine of phi sine of theta. We got the negative because the derivative of cosine is negative sine. Okay, so that's our partial h, partial theta.